We have a ruler which is having a length L and mass m, which is given a small angular displacement theta. Theta is small. This thing is going to oscillate now, and we need to figure out what the time period of that oscillation is. So it's going to be a little bit of practice of trying to figure out what the time period in different situations are. We already did the one with the spring, now let's do the one with the ruler. Okay, so let's begin. Start by making a drawing. So here is our ruler of length L and mass m. It's given a small displacement from the equilibrium position, and that displacement is theta, and it's given that theta is supposed to be small, and you will see pretty soon why theta has to be small. Okay, so in order to figure out what's going to happen, we need to build a differential equation. To do that, we need to use Newton's second law. Okay, so let's write down all the forces that we know are acting on this guy. And this has to be some sort of a nail or some sort of a pivot over there, right? Now if we use Newton's second law, if you try to figure out what the forces are, well, at the center of mass there's going to be gravitational force acting, and obviously there's going to be some force acting at this point, but you will see soon that force will not matter. Okay, alright, now what I'm going to do is I'm going to call this particular point as A. That's the point where the ruler is pivoted, and I'm going to try and calculate what the torque about this particular point is. So let's do that quickly. So let's write down Newton's second law for angular form. That's going to be torque. Also, I like to take the direction of the displacement as always positive. Notice that from the equilibrium position, the displacement has been anti-clockwise. So I'm going to call anti-clockwise as positive, and therefore if I have a clockwise, I'm going to call it as negative. Okay, so the Newton's second law is torque about any point you want, I'm going to call point A, should be equal to moment of inertia about that object relative to that point A times the angular acceleration that the object experiences relative to that point A. Okay, now what is the torque relative to the point A? Remember I told you there's one force acting over here? Well, that's not going to produce any torque. The only force that's going to produce a torque is mg, and we need to calculate the perpendicular distance between this point and this one. And that perpendicular distance is going to be just this length over here, this one. So what I'm going to do is I'm going to redraw this so that it becomes a little bit easier to understand the distances. So here is the center of mass, and the gravitational force is acting right at the center of mass. The center of mass must be right at the center. So this length must be L by 2. And we have this displacement, angular displacement as theta, and the torque is basically the perpendicular distance between this and this is basically this length. So notice we can use trigonometry for this little triangle, and this turns out to be sine, right? Sine theta is the opposite side divided by the hypotenuse. So this length, this perpendicular length, let me just call that length as r. We can calculate what that length is. Okay, anyways, so torque is going to be force mg multiplied by this perpendicular distance r, and notice that torque is clockwise. Can you see that? Torque is this way, clockwise, and clockwise is negative, so I have to put minus sign over here. That should be equal to the moment of inertia of a ruler relative to the point A. Now we already know what the moment of inertia of the ruler with respect to the center of mass is. It's a standard formula, you should remember that. But we want with respect to this point. So how do we do that? Well, we can use parallel axis theorem. Parallel axis theorem states moment of inertia about any axis you want should be equal to moment of inertia with respect to the center of mass. So that's going to be ml squared divided by 12 plus total mass multiplied by this distance square. Okay, revise your parallel axis theorem if you have a confusion here. Alright, anyways, this is going to be ml by 2 whole squared. And alpha, angular acceleration, is just the double differentiation of theta. So this is d square theta divided by dt square. Okay, let's see. We have m minus m g, and you have r, and r is nothing but L by 2 sine theta. L by 2 sine theta should be equal to ml squared by 4, ml squared by 12. You take a common denominator, you get ml squared plus 3ml squared times d squared theta by dt squared. Now here's where we can make an approximation. Since theta is very small, sine theta is almost equal to theta. So minus mgl divided by 2 times theta should be equal to, this is 4ml squared, that's ml squared by 3. Can you see that? 4 divided by 12, that's 1 by 3, right? So ml squared divided by 3 times d squared theta divided by dt squared. We're slowly beginning to shape this equation, and we're coming to the standard form now. Let's cancel out all the stuff that we don't need. We'll bring this on this side, and we'll now get d squared theta by dt squared into L divided by 3 plus g times theta divided by 2. I hope I've not made any mistakes here. Yeah, everything is fine. That should be equal to 0. Ooh, very close to the differential equation we need. All we need to do now is get rid of this L by 3. So just divide the whole equation by L by 3. So d squared theta by dt squared multiplied by 3 by L, okay? The whole equation. So let me write that. Take this whole equation multiplied by 3 by L. Alright, so I now get 3 plus 3 g by 2L times theta equal to 0. And look at what we have got. Look at it. That's a beautiful equation because it's of the form d squared x by dt squared plus omega squared into x equal to 0. Bingo. That's what we wanted. And the moment we have this, we know this fellow is omega squared. So let's write that down. Here is omega squared. Omega squared must be 3g divided by 2L. And so we wanted to calculate time period, if I'm not mistaken. Yes, time period. We can do that now. Omega is square root of 3g by 2L. Omega is 2 pi by t. And voila, there you have it. T equal to 2 pi square root of 2L divided by 3g. That's the time period of this particular system. See you next time.